Hi everyone. Today we're going to continue with our discussion about logs. We're going to work on three properties specifically. We're going to add, subtract, and take the power rule for our logs. So let's go ahead and get started. So the first one is, well, we learned a couple of rules last time, and one was rewriting logs, such as what we called it. We called it the change of base. So ones that we learned already were log base 3 of 5 can be written as log of 5 divided by log of 3. It turns out it could be any base you want. You could write log base a of 5 over log base a as 3, as long as they're the same base. Log of 72 of 5 over log of 72 of 3. Right, so it doesn't matter what the base is. And normally we just switch that to a common log, which is base 10. Okay, that was our change of base. And on your calculator, whether you type, let's say you want to find this answer, log of base 3 of 5, whether you write log base 10 or natural log of 5 over natural log of 3, that would actually be the same answer. Okay. Today we're going to jump through something a little more easier. The idea is logs don't act the way we think they should. Because we normally add like numbers like 1 plus 2 is 3, and those are all kind of on the same level. They're just regular numbers. But exponents act differently because they're counted differently. Now let's talk about some exponents that we know about before. If I say 3 squared cubed, what happens to the exponent? Do we add or multiply them? We multiply them. But if I say 3 squared times 3 cubed, do we add or multiply when I'm multiplying? And this is the product of powers, which says we add the exponents. So these rules are different for exponents, and that means they're different for logs. And our first rule today is our addition property. Addition property for logs. So that's add logs. If I say log of 3 plus log of 2, these both being common log, being base 10, this actually becomes log of 3 times 2, which can be written as log of 6. What? I thought we're not allowed to combine stuff in this way, right? But logs are their own little creature, and we have to know our rules for logs. So if I'm adding logs on the outside, I am multiplying them on the inside. Let's try this with another problem. If I say log of x plus log of 2, normally we would say, hey, you can't combine them, they're not like terms. And you're right, they aren't like terms. They're their own individual logs, but our log rule says, hey, you can always write this as 2x, multiplying logs together on the inside. So what happens on the outside is reflected differently than the inside. So when I'm adding logs on the outside, I am multiplying logs on the inside. And this could be kind of confusing if you don't remember the rule. What if I want to spin this around? If I write log of x times y times z, we could split this up into 3 separate logs. Log of x plus log of y plus log of z. And is this a rule that seems very easy? It's like, duh. But it's a rule that we needed to call out. We needed to define this rule. And then we also need to remember this rule, because we're always going to forget it, and it is confusing. When do I add? When do I multiply? When do I subtract? And exponents had their own rules that way. Now, why is it when I'm multiplying, I'm adding? Okay, why is it when I'm multiplying? See how I'm multiplying here? Why is multiplying adding? It actually turns out this goes back to what logs really are. Let's look at a basic example. If I say log base 2 of 8 is equal to 3. You guys okay? Logs. Circle of logs. 2 to the third power is 8. So each of these parts of a log are not what we traditionally would think of. We have a log with the base. And then this is why I like calling the answer is equal to the exponent. Okay? So base exponent answer. Now, I want to actually take us back to a problem that we just did previously about what happens when I'm multiplying logs. So if I give you 3 squared, okay, is equal to 9, right? That's what 3 squared is. If I rewrite this as a log, it's log base 3 of 9 is equal to 2. Okay? So the idea here is this is the answer. Okay? So what happens when I'm multiplying a couple different answers? What if I'm writing log of 9 times 27? Let's look at it this way, right? We can write 3 here if we want. Well, couldn't we break this up? Well, our rule says, well, if I'm multiplying, I'm really just adding. But how is that possible? Why does that work for us? Well, I want you to think of it a little differently. Let's take a look at what happens if I'm writing logs in a different way. Well, what if I say this is 3 squared and 3 cubed? Would you be okay that 3 squared times 3 cubed is really 9 times 27? And what happens when I'm multiplying powers? We add the exponents. And guess what? Logs solve for exponents. These are actually exponent answers. Because logs solve for exponents. So the log that we're dealing with here is that I'm actually adding exponents. See, exponent plus exponent. If I'm multiplying the product of answers, means I'm adding exponents. That's why when we're multiplying inside, because these are the answers, right? This is really 3 squared and 3 cubed. We end up adding the exponents. And that's a little hard to wrap your head around, but this is the reason why logs, if I'm multiplying on the outside, if I'm adding on the outside, I'm multiplying on the inside, because that inside answer is R9 and R27, or is our 3 squared and our 3 cubed. And if I'm multiplying those, we end up adding the exponents. Okay, so it really stems back from this rule here. If I'm multiplying answers, I'm adding these exponents if they have the same base. And that's why logs add exponents, because logs solve for exponents. That's the fundamental reason why. If not, you can just memorize it. Let's give you guys another one. If I say log of 3 times a times b, this is going to be log of 3 plus log of a plus log of b. Okay, so that's the rule. If we're adding logs on the outside, we are multiplying them on the inside. Or if I'm multiplying them on the inside, we can break it up into separate logs. Now, why would this be helpful? If I write log base 3 of 27, a, if I want, I can separate this. Log base 3 of 27 times plus log of a. What is 3 to what exponent is 27? That's just 3. So maybe we want to rewrite it. We want to simplify it a little bit. Now, here's our next rule. If you think adding is multiplying, well, then what do you think subtraction is? Now, if I say log of b over a is log of b minus log of a. Now, I want you to notice that the negative log only applies to the denominator. Whatever is on the denominator gets a negative sign there. And we'll explain that in our next rule, why that's true. But if we're dividing inside, we're subtracting on the outside. If I'm subtracting on the outside, take a look here. I have two negative logs. These are both subtracting. So this can be rewritten as x over y and z. X over y and z. Okay, so it's a lot to remember. But if it's dividing, we're subtracting on the outside. If we're multiplying, we're adding on the inside. Okay. Let's give ourselves another one. If I say x, so log of x plus log of y minus log of z plus log of a. Take a look, there's a lot of plus and minuses here. But when we're subtracting logs, that's the one that ends up on the bottom. So we can combine them. Log of x times y times a all over z. Okay. Now, our last rule today is our power property. And this is, I would say, the most useful rule for logs. This is like kind of what we're getting to. And the rule simply says if I'm taking the log of an exponent, that exponent can be moved to the front. It brings down the gods. It brings down these exponents, which is super important for us. And I'll illustrate why it's important for us in just a little bit. So the idea here is logs bring down the exponents. As you can tell, I brought down the exponent here. And now the exponent is in the front. Log of 3 to the x plus 2. Guess what? What does it do to the exponent? You guys move to the front. X plus 2. Log of 3. Log of 5 to the x squared plus 1. That's x squared plus 1. It doesn't matter what's going on there. It always brings down the exponent. It goes backwards too. If I have a number 5, log 3 plus 4 log 2. Okay. We can rewrite this. Where does this log, where was it originally from? Well, it was really supposed to go up here. Where was the 4 really from? It was actually just for the 2. So the exponent only goes to that one value on the inside. This is log 3 to the 5th plus log 2 to the 4th. Okay, so you can see we moved up the exponents first, so we're not confused. Now our rule says what's a log plus a log? If I'm adding logs on the outside, I am multiplying them on the inside. And if I'm adding logs on the outside, I am multiplying logs on the inside. Let's make this problem a little harder. 4 log a plus 2 log b minus 5 log c. Now we're kind of mixing all the things that we've done today around to each other. So before I start combining logs, I need to get rid of this 4, 2, and 5. That's log base a to the 4th plus log base b squared minus log of c to the 5th. See, I just moved the exponent to the top. Now we can follow our rule. If I'm adding, I'm multiplying, and if I'm subtracting, I'm dividing. Log a to the 4th times b squared over c to the 5th. So we can combine our logs, no matter how messy they are. If it's adding, we're multiplying. If it's dividing, we're subtracting. And kind of anything in between, right? We can move the powers down. Okay, now that we have a lot of rules for logs, let's see where logs would be useful. Now, let's see if I have a problem that says 3 to the x is equal to 81. We all know that 3 times 3 is 9, times 3 is 27, times 3 is 81. Turns out 3 to the 4th power is 81. And that's one way that we solved this before. We said 3 to the x is equal to 3 to the 4th power. That means since the bases are the same, the exponents are the same. And that's one of the tricks we used to solve these problems before. But let's say I want to use my calculator to solve for this, because maybe it might not be 81. Maybe it's a number that isn't a multiple of 3. So here's what I'm going to do. The trick is to actually use logs as a tool, because we have no way in algebra to solve for exponents if the variable is in the exponent position. So this is up here. We have no way to solve for that. So here's what logs do. What do we say logs do to exponents on top? Where do they move them to? It moves them to the front. X log of 3 is equal to log of 81. Now log 3 is just a number, it's not some random variable. So we can divide this over, log of 3 to both sides. X equals to log of 81 divided by log of 3. Now if you guys type this on your calculator, if you guys have a calculator nearby you, if you type log 81 divided by log 3, it will actually give you the exact number 4. So we just worked on a tool of solving for exponents, something that we were not able to do before. And we used a couple of the properties that we talked about. Now here is also something else. If you want instead, you could rewrite this as a log using our definition. How to write this as a log? Log, what's my base? Is it 3x or 81? It's going to be base 3 of the answer, 81, is equal to x. Circle of logs, 3 to the x power is 81. And I want to show you something kind of cool. That isn't log base 3 of 81 the same thing as log of 81 over log 3? That's just the change of base version of it. Remember, we can always write log of 81 over log 3. So we can use our straight identity, or we can go through the process of using logs as an algebra tool to solve for this. And really, that is our process. Okay. All right, so today we're going to get to this some more a little bit later, but you guys are going to be working on your iExcel stuff, and that's it.